Hi everybody, Cal here with sections 2.1 and 2.2. Section 2.1 is talking about matrix operations. As a general setting, now that we're in chapter 2, what we're going to start doing is divorcing ourselves from having a system of equations in the background, system of linear equations, and we're going to start looking at matrices for their own sake, maybe as the matrices of linear transformations, maybe just as an object worthy of study on their own. We're going to start 2.1 with a number of light definitions having to do with matrices. It'll talk about the entries of a matrix and how the numbering is going to work. Usually we'll index them with two different numbers. So Aij, which you'll see over here, is the entry in the ith row and jth column. You can also think of a matrix as having columns, bold A1 through bold AJ, I suppose, AN, I suppose that is. We can talk about diagonal entries, the main diagonal of a matrix, what a diagonal matrix is, and these are all notions that you should be aware of. You've already been introduced, by the way, to the identity matrix in a previous reading. That's the matrix with ones on the main diagonal and zeros everywhere else. Square matrix, of course. Here we talk about sums of matrices and scalar multiples of matrices, which should seem a lot like sums of vectors and scalar multiples of vectors, and that's no mistake. Example 1 will play with those concepts, as will example 2. Theorem 1 gets into the algebraic properties of sums and scalar multiples of matrices, and these should come as no shock to anybody. Then we get into matrix multiplication, which is a little bit different. I would read through this discussion reasonably carefully, and I would go through the bottom of the page and into the definition over here. Just like with matrix vector multiplication, this is not a good computational definition, but it is a good theoretical definition, and one that will come up in your homework from time to time. Go ahead and go through example 3, where it computes a matrix vector product. The blurb down here is useful. I would pay attention to example 4. What is the size of a matrix-matrix product? But I would really be looking towards the row-column rule for computing a matrix-matrix product. This is very similar to the row-column rule for a matrix-vector product that we discussed in section 1.4. Example 5 will go through using the row-column rule to multiply matrices. And I would practice multiplying matrices. Just take two matrices of sizes that will multiply and just practice figuring out what their product is. That's going to be worth your time. This is something that you're going to want to be able to do quickly and accurately. Examples 5 and 6 kind of go through a little bit of the computation inherent here. Theorem 2 is more properties of matrix multiplication. This is important stuff. We have an associative law, distributive laws, and so on. Take a look at how the identity matrix works. This might be a hint for why it's called the identity matrix. And I would pay careful attention to example 7. Take a look at how AB and BA are two different things, and these warnings down here are super duper important and inform a lot of how matrix algebra works. So do take special note of those. We talk about powers of a matrix, which should seem relatively obvious. We also talk about the transpose of a matrix, which is something new. I would go through example 8 carefully and make sure you understand what a transpose is and how they are finding these. Theorem 3, properties of transposes. Most of these should seem really obvious. Part D might not seem obvious and is worth your time to look at. The blurb at the bottom of 101 encapsulates 3D, and you do want to know Theorem 3D. In fact, there might be a question about it sometime in the near future. That ties up section 2.1. 2.2 gets into the inverse of a matrix. One of the things that you may have noticed in the previous section is that they didn't talk about division of matrices, and that's because there is no such thing as division of matrices. The best you can do is multiplying by an inverse, if an inverse exists. And it does not always exist for any matrix. You want to first of all know the definition of an invertible matrix and the inverse of a matrix. This blurb over here, the second full paragraph of 105, gives you the definitions, and you do need to know these. I often test on them. We will use the term singular and non-singular. They're not going to be like central or anything, but they'll come up. Theorem 4 tells you how to find the inverse of a 2 by 2 matrix. It is not useful outside of that context, but it is useful there. This is also our first hint at something called the determinant, which we'll study later on in the course. Don't worry about it too much for now. Example 2 lets us use Theorem 4 to find an inverse of a matrix. It's not terribly interesting. Theorem 5 is interesting, and the proof is maybe more interesting than the theorem itself. I would look at the proof of Theorem 5. Also think about what this says about where the pivots have to be in A, if A is invertible. If AX equals B, A has a solution for every B, and if the solution is unique for every B. This says something very specific about where the pivots in A are. You don't have to spend too much effort on example 3. I might actually just kind of skip that over. It's not terribly important for us. Example 4 is a direct computation about the previous theorem, about Theorem 5. Theorem 6 is going to be useful, some algebraic properties of inverses. And this is going to come up, so take a good look at that. In particular, 6b is something that you need to know, and it's encapsulated in the blurb here at the top of 108. You don't have to pay a lot of attention to the part of this section on elementary matrices. They're used to prove a little bit of stuff. If you're a math major, do spend some time here. Otherwise, it's probably not going to be that important for you. So let's kind of move on past that. You know, you might want to give that page and a half a read, but it's not going to be terribly important for us. I'll talk about it a little bit if we have time. Theorem 7 is super important for us. This tells us how to find the inverse of a matrix in general, and how to tell whether a matrix is invertible. The proof uses elementary matrices. In fact, it's the only real reason that elementary matrices are important. But they are important for this proof. This is a pretty big one. Again, we're going to use Theorem 7. We're not going to be so interested in proving it. So, and the theorem informs this algorithm for finding A inverse. So make sure you understand the algorithm. Go through example 7 that comes after it. You could read this blurb at the end, another view of matrix inversion. It's not going to be so important for us. I just want you to know what an inverse is and how to find it. That's the main takeaways from this section. And I want you to have a hint that inverses are useful in matrix algebra, because we need them instead of division, which we don't have. So, that's these two sections, and I'll see you next time.